Minasan, konnichiwa, Zamurai Engineer desu. In this video, let us again talk about simultaneous linear equations using Gaussian elimination. And this is the fourth video on this topic, wherein we already discussed the concept and procedure in doing this method. We already presented one example, and we already introduced what are the possible pitfalls. So in this video, we're going to tackle how to countermeasure the pitfalls. So that is by using Gaussian elimination with partial pivoting. So pitfalls of the Gaussian elimination are possible division by zero and large round-off errors. By partial pivoting, we are going to be able to avoid those pitfalls by increasing the number of significant digits. It will decrease round of error and does not avoid division by zero. Okay. Gaussian elimination with partial pivoting avoids division by zero. It also reduces round of error. So instead of just increasing the significant digits, which do not counteract or avoid the division by zero, we are just going to use partial pivoting instead. Okay, so this is our solution. Okay, what is different about partial pivoting? At the beginning of the kth step of forward elimination, find the maximum. So we have the absolute value a k plus 1, k, and so on up to a n k. So if the maximum number of values is a pk, meaning fifth row, so we are on the fifth row. We are on the p row, okay, wherein p is between k and n. Then switch rows p and k. Okay, we can switch the rows. Okay, so let's do that. For example, a big square matrix like this, it will form at the beginning of the second step of forward elimination, because at the beginning of second step of forward elimination, we have the following matrix form. Take a look at the first column. So A11, we have 0, 0, 0, and so on up to 0. So we have what? N different equations. In fact, A11 up to ANN are the coefficient. We are very much concerned about this coefficient, because this coefficient will determine if we are actually doing the elimination process correctly. Okay, so example, second step of forward eliminations. So we have the following, for example. This is what? A 5. Okay. So how many? 1, 2, 3, 4, 5. So 5. 5 by 5 square matrix. Okay. So which two rows would you switch? Okay. So we need to switch the rows in order to avoid the what? The two pitfalls. Okay. Okay. Looking at this, we need to have a way, a procedure, a rule, so that every time we encounter such possibility of falling into the pitfalls, we are going to be able to avoid it. So there must be a scientific rule. Switch rows. Okay, so which rows did you switch? Okay, which one? The second row and the fifth. Second row and the fifth row. Okay. Okay, we switch second row and fifth row. Okay. Second row and fifth row. Take a look. Second row, 0, negative 7, 6. Fifth row, negative 17, 12. So it will be switched. Negative 17, 12 will be going to the second row. Okay. Okay. We are able to switch. Okay. Okay. A method to solve simultaneous linear equation of the form, again, by our Gaussian elimination method with partial pivoting, we have two steps. The same, forward elimination and back substitution, but we have forward elimination, same as the naive Gaussian elimination method, except that we switch rows before each of the n-1 steps of forward elimination. We are what? Manipulating the arrangement, to avoid pitfalls. Okay. Example matrix form at the beginning of second step of forward elimination. Okay, so second step, because we already eliminated the first coefficient of all of the rows except the first equation. Okay. So this the format that we would like to get into. This is our goal. This is our goal, to create what? Upper triangular matrix. And back substitution, starting equation would be like this. So after we are able to successfully done the triangular matrix, we are now going to back substitute. Okay, so these are the same, but we implemented what? Switching of rows. Okay, so it's like this and like this. The same equation, the same scary equation come up here. But this is not so scary on real application. If you apply it, it is not so scary. It is scary looking. It look like it's scary, but it's not. So we switch. So pivoting meaning we would like an equation to be switched to the point wherein we need the pivot. We need the pivot. So we need the pivot here because okay, we are now going to start the second equation. So the pivot is the coefficient that we need to what? Manipulate by dividing and multiplying. Take a look. And actually, this is the pivot because we want to use this to eliminate 4, 9, and 17. We want to use this. This is the pivot. We will actually retain this equation, but we want to use this equation in order to eliminate all of this. Okay? So, for example, at the very start, okay, at the very start, first operation is to eliminate this. What is the pivot in order to do this? Elimination of the first coefficient from the second equation up to the last. This is the pivot because we divide all of the equation 1 terms, including the constant here, divide by A11 and then multiply by A21. Okay? And because of that, the resulting equation has to be subtracted to equation 2 and it will become 0. Okay, so that's all that matters. That's why we call it pivot. This is the pivot component. This is the pivot unit component. Okay. So it is the pivot 1. So here the pivot 1 already used was the 6. Now we have the next pivot, -7. But here it is shown in the problem that we have to switch. We have to switch. Now, another practice for you. Solve this from this point. Solve this. So you need to what? To eliminate 4, 9, 17 so that it becomes 0. Then after which, eliminate this one, and eliminate this one. So that you can have what? A small triangle of zeros, and therefore you have the upper triangular matrix. That is the goal of forward elimination. And because of that, you will notice that it will encounter the pitfall. Okay, it will encounter the pitfall and will not be able to overcome the pitfall. However, in this recommendation, the solution is recommended to be switched, equation 2 and equation 5. So solve it again using the switch. So this is now the switch. This is original. This is the switch. Okay. So switching that, we did not change. If we have an equation and just switch the location of the equation, we did not change the problem. We did not change the problem. We just named the equation 2 to be the equation 5 and rename equation 5 to be the equation 2. We just naming. Okay? Doesn't change the problem. So it is a perfectly valid manipulation. So there are 2 tasks for you to practice. Solve the original matrix and then solve this switch rows matrix. Okay, and then let us compare. You have to compare the answer. The answer should be the same. Answer should be the same. Meaning x1, x2, x3, x4, x5. So the values of those variables should be the same. Okay, because we did not change the problem. They will change the result if we change the problem, but we did not. So the same result should come out. Okay, so so this is the end of forward, and let us do the backward elimination. So the same thing is going to happen, but you have the task to practice. Okay, and I will get your answer for that. Okay. Again, this is Dr. EYPEI, preaching engineering for nation building.